Now, okay, now we have seen about flames, but how to get some height correlation for a fire, real fire basically, because till now what we have seen is the gas jet coming out. In the laminar regime, how will the flame height vary? In the turbulent regime, how the flame length will vary? But in fire, we don't usually involve gaseous fuels alone. So it may be basically solid fuels, liquid fuels, etc. So it is normally useful if the height can be correlated to heat release rate of the fire, which actually depends upon the burning rate of the fuel or the mass loss rate of the fuel. In the condensed fuel, there is no flow rate, no. So that how the, see, given initial mass of the condensed fuel, how the mass is lost as the fuel burns, that will give you the mass loss rate or the burning rate. Multiply that with the heat of combustion or the calorific value of the fuel, you will get the heat release rate. So there are several correlations available in this. Okay, now the advantage of doing this is when you have the correlation between heat release rate and the flame height, when you see the flame height, it is possible to get back the heat release rate at least approximately. There is a coupling between the heat release rate and the flame height, because higher the mass loss rate, higher the burning rate, higher will be the flame height, higher will be the heat release rate also. So that is the concept. So there are several correlations available in literature. The few of them is listed below. The first one is very early 1961 Thomas correlation, where you can see that LF is 42 times D, some empirical constant. D is the fire diameter, that is surface area divided, we can say length scale got from the surface area, into this m dot double dash is the mass burning rate per unit area, flux of the mass burning rate, divided by the ambient air density into a velocity scale. This root of dg is a velocity scale. So again you can see that g is meter per second square and this is meter, under root will be meters per second. So this is the velocity scale. What is this velocity scale represent? That is the buoyancy induced flow. Due to the gravity, the buoyancy induced flow, some velocity scale. So this denominator is rho into a velocity scale v, which is again a mass flux. Rho into v is a mass flux. So this quantity is non-dimensional. Okay, some empirical power also is given to this non-dimensional quantity. So LF depends upon the mass loss rate, which is non-dimensional and made non-dimensional, but we can see that LF depends on D, that is the diameter of the fire. So that means in the fire case, which is basically a turbulent diffusion flame, the dependence on LF on D is clearly given here, but to correlate, the mass loss rate is also included. If you multiply this mass loss by delta Hc, you will get the heat release rate. So easily heat release rate also can be correlated to this by adjusting the constant and so on. This is one of the correlation. Then the second correlation is developed on proposed on 1983, Heskested correlation, where he has used heat release rate to correlate in kilowatts. Please understand this heat release rate in kilowatts, and this 2 by 5 power actually comes due to the fact that when you have some non-dimensional number based upon q dot and its power is 2 by 5, this will go as a length scale, length scale L. So again you can see that this is correlated using the heat release rate, and a diameter term also is present here, again indicating the importance of the flame length on the diameter of the fire, as the scaling analysis has shown us. Similarly, For wall fires, see if there is a vertical wall which is actually burning, okay, the wall is burning, then the wall fire, there is a correlation for the flame height which is 0.174 into some constant into q dot. This is another empirical constant based upon the configuration into heat release rate power 0.4. So, we can see that in order to determine the height of the fire, we can use the mass loss rate or the heat release rate and propose correlations for several configurations. Okay. So, these are the important correlations. We can also find several correlations in literature. Now, let us go to important thermophysical properties which are to be used in the analysis of the fires basically. So, density, dynamic viscosity mu, thermal conductivity lambda, then specific enthalpy, specific heated constant pressure Cp and the mass diffusivity. These are all important physical and thermal properties which are to be used in the calculations. However, these properties are strongly dependent on temperature. So, how to calculate these properties and use them? See, for example, we have talked about several non-dimensional numbers in the first module in which these properties are used. So, how to calculate the value of these properties when there is a dependency on these properties on temperature and there is a temperature variation in the flow field also. It is not an isothermal flow field, correct? Reactive flow field. So, basically what we can do is density can be calculated using ideal gas equation of state, assuming that the density values are low enough because of the fact that the temperatures are quite high or the pressures are not very high. So, P equal to rho RT. So, R is the mixture's specific gas constant. Okay, that is obtained as Ru divided by molecular weight of the mixture. That is the density way you can calculate this. So, directly mixture's density can calculate. Dynamic viscosity, thermal conductivity, specific enthalpy and specific Cp etc. can be calculated using some polynomials of temperature which are actually reported in literature or the NIST database etc. We can use that. And once for individual component you find these values, then you can use mixing rules. For example, Cp of the mixture can be calculated as sigma yi Cpi, where this is mass fraction. So, this Cp is in joule per kg Kelvin. So, when you have a quantity which is on per kg basis, then mole fraction into that Cp should be calculated for each species and summed up for all the species to get the mixture value. Okay, now mass diffusivity. So, similarly you can do for others also. There are several literature which will give you the equations and the correlations. For example, Cpi itself can be calculated as a polynomial of temperature, is a function of temperature, non-linear function of temperature. We can calculate that individual Cp's, then find the mixture Cp. Then mass diffusivity, basically you can see that when I say mass diffusivity, we think of a binary diffusivity of a component A diffusing into component B. So, when you say this, it has a unit of meter square per second. It shows that how fast the component A can diffuse into component B. Basically, the same rate the component B also will diffuse into component A. So, here kinetic theory basis is available to calculate individual pairs of mass diffusivity, taking any two components together, and this is evaluated as a function of both temperature and pressure. Once that is done, then D of A into mixture can be calculated using these individual things. So, for example, there is a certain rate at which the component A goes into a component B, but when several components are present, there is a certain rate at which component A will go into the mixture itself. So, that is calculated using the mole fractions of each component and this individual, so I will say Dij, and using this there is some functionality between these two to be used to get this. So this is the function of these two basically. Okay, so the thermophysical properties are strong functions of temperature, and the individual properties have to be evaluated, and mixture properties have to be determined to do the analysis. Now, diffusion coefficients. So mass diffusivity we have talked about. Similarly, kinematic viscosity, which is nothing but the dynamic viscosity by the density. Similarly, alpha, the diffusivity, is lambda by rho Cp. These can be calculated because all other properties are known to me, so we can calculate this. And some simplifications also can be done basically. So to understand the simplifications, let us understand some non-dimensional numbers. First one is Lewis number, which is the ratio of thermal diffusivity to the mass diffusivity. Prandtl number, see there are three diffusivities. So Lewis number takes into account of the ratio of the thermal to the mass. Prandtl number is nu by alpha, momentum to energy. Then Schmidt number is nu by d. So if you evaluate one of these properties, then we can invoke assumptions like all these non-dimensional numbers are same. That means even in the laminar regime, the diffusivities are not going to vary much. But in the turbulent regime, it is definite that this will not vary. But laminar regime, it is not very easy to fix this like this. But to simplify our calculations, we can do that. But since the turbulent fires are turbulent in nature, this invoking this will not be a big issue for us. Then one more thing is Cp for all the species is same. That means just take the major component like nitrogen, evaluate the Cp at a particular temperature and use it. So that is another simplification which we can do. So here Cp can be say Cp of nitrogen at a given temperature T approximately. Now let us also understand some controlling factors of combustion or fires. Okay, first one is when you have some process which is controlled by chemical kinetics. The examples are ignition. When you want to ignite something, chemical kinetics plays a role. Why? Because if you have a say pool of liquid fuel and it vaporizes, forms a mixture. So vapor comes out, air comes out and forms a mixture. When you ignite this mixture, basically a flame forms. So now we are talking about premixed combustion, where the fuel vapor has mixed with the air and reactant mixture is formed which is ignited. So premixed combustion is dependent on the chemical kinetics because there is no mixing etc. Already it is mixed. To ignite it, you need a mixture of certain volume and an energy source of certain strength. Then you can ignite it, where the chemical kinetics alone will play a role. Similarly, explosion, when we have a premixed mixture in a rigid vessel, constant volume vessel, and you ignite it, then again it depends on chemical kinetics. Pressure builds up, temperature builds up, pressure builds up, and explosion can occur. Similarly, when the flame is quenching, okay, then also you will see that the chemical kinetics plays a role in extinction. So in this extinction, for example, I can say that here, when the fuel jet is coming out at a higher velocity, I told that a lifted flame can be formed, lifted flame. So this is lift off height. So this is like a local extinction, correct? Local extinction. Here there is no flame. So it's like a local extinction. But the fuel comes out here, mixes with oxygen or air from the atmosphere. So it is like a premixed combustion. So extinction, local extinction like lift off or quenching, etc., needs chemical kinetic information. So the first certain processes in fire involves the analysis assisted by chemical kinetics. That is the first set of category. Second one is which is controlled by physical mixing processes like diffusion, flow and turbulence. There is no chemical kinetics useful for this. Examples are pool fires. So, when there is a pool of liquid fuel and it is ignited, then a fire forms, correct. Sustain when the, of course, the temperature is more than the fire point and the liquid fuel entire surface is occupied by the fire and the heat feedback comes, mass transfer comes. So, this flame sustains. So, the fuel is transported from the fuel surface, the vapors are transported to the flame, oxygen from the ambient comes and the flame sustains here. It is only the mixing of fuel and fuel vapor and the oxidizer. So, the flame forms wherever the fuel and oxidizer are mixed at stoichiometric proportions, as we have seen in the diffusion flames. So, there is very little for the kinetics to do here. Similarly, open fires, flame of gaseous fuel jet, we have already seen this. Then liquid fuel spill, sprays and droplets. Even a droplet, say individual droplet, when it comes and burns, see where it can happen when there is a for example, if the liquid fuel comes out through a leak etc. and forms some droplets and burns in an environment, then this droplet will vaporize based upon the convection and fuel vapors come out from the surface, oxygen from the ambient comes out and a flame is formed over this. Again, this is diffusion control, how fast the vapor and the oxygen from the ambient mix, the flame zone will appear there. Little role played by the chemical kinetics. So, carbon particle and burning of candle etc. also contribute to the second category where the transport processes, you can say transport processes play a role. The first one is chemical kinetics play a role, transport process does not play a role. The second, transport processes play a role. But there are certain categories in which both chemical kinetics as well as the physical mixing play a role. Okay. So, where? Compartment fires. So, if you have a compartment fire with some limited ventilation, there may be some burning initiated in some particular commodity, then the air which is present can be consumed partly, then another commodity may be ignited, but in some cases this heat from one of the commodity can heat up or make the other commodity to pyrolyze, and some premixed pyrolysate or the gases which are coming out can form a mixture with the air and this mixture can burn. That means initially it starts with a non-premixed combustion, but it may lead to a premixed combustion also. So, both kinetics and physical mixing are important. Similarly, Bunsen burner flame where you allow some air also to come in, partially premixed flames, then gasoline engine etc. So, these are the examples where if there is partial premixing and there is a combustion in non-premixed mode also, then both will play a role in several applications. So, now these are the three categories, that is in first category only chemical kinetics play a role, there is no role for the transport processes. In second category, transport process alone play a role, chemical kinetics is extremely fast. So, it does not play any role. Rate controlling is what? The rate controlling step is one which will take the enough time to complete. Okay. In the case of the first category, already premixed things are there. So, mixing will not play any role. Only the chemical reaction time plays a role. In second category, the mixing time is very important. Chemical reaction time is very, very fast. So, the mixing time is going to dictate the overall time. So, that is the controlling factor. In some cases, both will contribute. Now, let us understand how to calculate the chemical time. The chemical time is the time taken for the reactant. So, for example, what is the reaction rate for a reaction between A plus B? The rate at which the concentration of A changes with time, it is negative because the A is a reactant and decreases. So, initially A has a concentration of A suffix 0 and this depletes. It As it depletes, the concentration decreases to a value of A at a certain time t. Now, if the concentration of what is the time it takes for the A to reduce to 1 by E of the initial concentration, that time is called chemical time. Okay, very simple. So now I can find this chemical time as if omega triple dash A, which is equal to minus dA by dt. This is the rate at which A reduces. So it is actually kilomole per meter cube second. So this is the reaction rate. Then I can say the chemical time Tc will be equal to what? Concentration of A divided by the reaction rate, that is kilomole divided by kilomole per meter cube second. So here I have to also use, this is kilomole per meter cube concentration. So you can see this is second, meter cube second. Okay. So that is the chemical time. Okay. So now for diffusion dominated, so then another characteristic time is called residence time of the reactants. See, when if you see the flame which is coming out of a anchoring towards the port, then it means that the reactants which are formed very near to the port has time to burn there. When you take a lifted flame, it means that the reactants has no time to burn within the certain length from the port exit. So that means even when the mixture is formed and the mixture is flowing at a velocity, the mixture at a particular location may not reside up to a given time where the chemical reaction is complete. So the residence time means that the mixture has to stay at a particular location until the chemical reaction time completes. So that is called residence time. So this TR can be calculated in two ways. First case is low flow velocity. If you take a low flow velocity, the residence time or physical time will be L square by D, where D is the mass diffusivity. So you can say a meter square by meter square per second. So this is the time scale. When you have a convection, okay, then there is a velocity u involved, flow velocity, and there is a characteristic dimension L. So time can be calculated as TR can be calculated as L by U. So TR is either L by U or it is L square by D. So I can calculate the residence time, which is also called physical time. Residence time is also called physical time. So now with these two time scales, residence time and chemical time, or physical time and the chemical time, I introduce a important non-dimensional number called Damkohler number, which is ratio of chemical time to the physical time or the residence time. Damkohler number TdA equal to Tc by Tr. So we can also use the reciprocal of this. So now let us say chemical time is much greater than the residence time or the physical time. That means already everything is fixed, mixed well. There is no physical time required for mixing. Only chemical reaction has to take place. So obviously when this time scale is negligible, this time scale is going to dictate the process. So the particular phenomena will be kinetically controlled. So when the reactants are thoroughly mixed, the gradient in species and temperature are zero because they are already mixed. So the rate of depletion of the reaction mixture is dictated by the how fast the flame propagates through the mixture. That means it is kinetically controlled. Here dA equal to Tc by Tr. Since Tc is much larger than Tr, it is greater than 1, much greater than 1. So large Damkohler number constitute to defined as Tc by Tr contributes to higher the higher value of Damkohler number contribute to kinetic control regime. In the extreme case, Tc is now less, very less than Tr. So that is, I have a diffusion flame. Fuel comes from this, oxygen comes from this. Whenever they mix that stoichiometric proportion at a particular location, they immediately react. Kinetic time or chemical time is much smaller than the physical time where the reactants go and mix to the stoichiometric proportions. So this is transport control, mixing controls. So here the reactants are mixed only at the flame zone, and the gradients of species or temperature etc. are very large. So we can already see we already seen there's no oxygen comes from this and goes like this, reactant comes from this and goes like this, and this is the flame zone basically. So the gradients are very large. So here the rate of depletion of the reactants is dictated by the relatively slower transport rate. The chemical kinetics is very fast. So here the Damkohler number is very small, defined as Tc by Tr. But in the third category, where the combustion phenomenon is controlled by both, we can see that the chemical time will be of the same order of the resident time or the physical time. So these are the three modes we have to understand. So that means when you want to capture ignition or extinction etc., we have to calculate Damkohler number. Any instability for that matter, Damkohler number is very useful number for us to correlate. Okay, so these are the important parameters we have to remember when you analyze both premixed as well as non-premixed, because fire scenario can give you both the modes, premixed mode or non-premixed mode, or we can also say partially premixed mode also will be resultant from that. Okay, so that is very important for us to understand. So I will finish the lecture here. We will go to the next model next time.